Okay, so the last piece of the puzzle in our discussion of concurrency is just going to be a quick synopsis of the history of concurrency support in Java. And you may know some of this, you may not. By the end of this overview, you'll know a bit more about the ways in which Java concurrency features have evolved over time. So right from the very start, from the first version of Java, which came out in springtime of 1995, Java threads and something called Java built-in monitor objects were available right from the start. So Java 1 had threading built in from the beginning. That was kind of cool because at that time there weren't a lot of other programming languages there weren't a lot of other general purpose, widely adopted programming languages that had robust support for concurrency. The focus at that stage was on basic multi-threading and synchronization primitives. So you had this concept of threads. So let's take a look at a simple example here. This example can be found here at my website. And this example had simple blocking bounded queue, which is a version of the buggy queue we looked at before that's actually works properly. And so we would make an instance of that, and then we would create one thread that would be going to be producing messages. Another thread was going to be consuming messages. And so we would have this simple queue passed to both producer and consumer, so they would share it. And then we go ahead and we start those threads, basically using a Java for each loop to start each thread. When they start, they'll start producing the data. And then while those threads are off and running, the calling thread, or the main thread perhaps in this case, goes ahead and waits for the other threads to finish by using what's called join. And this is a simple example of a barrier synchronizer. So we're going to join things together. So very simple, nothing too complicated in Java from the start. The other capability that Java had right from the start were very basic synchronization primitives, in particular something called a built-in monitor object. And again, this goes beyond really the scope of this course, but a monitor object is a pattern that enables multiple threads to take turns accessing the shared data within a critical section, and also allows threads to coordinate their interactions by either notifying or waiting for things to happen. So let's take a look at a simple example. Here's the take method on the simple blocking bounded queue, and this demonstrates Java's built-in monitor object and mutual exclusion and coordination primitives. So take, what its semantics are, it says wait for something to show up in the queue, and then take it. If there's something there, we'll take it right away. If there's nothing there, we're going to wait. So what take does is it acquires what's called the intrinsic lock. Every Java object has a lock, which is intrinsic lock. And this synchronized this basically says, wait until I have exclusive access. No other threads are in that critical section. It's like the restroom in an airplane. And then while the queue is empty, while the list is empty in the queue, wait. And what wait does is that goes ahead and releases the intrinsic lock and puts the calling thread to sleep until another thread comes along and puts something in the queue and wakes it up by notifying it. So after we've had a chance to get an item in the queue, so this will keep looping until the queue is not empty. At that point, we're going to call notify all, which tells everybody I'm taking something out of the queue, so if you want to put something in the queue, there will potentially be room for you now. And then the very last thing that happens is we remove the item and return it, and the intrinsic lock is released logically released when the closed curly brace is reached here. This is what's sometimes called a synchronized block of code, and it uses basically it's a scoped locking pattern that's common in languages like Java or C++, using various features built in those languages. So those are very, very simple primitives. They're efficient, but they're low level. They're very limited in capability. There's a whole bunch of things you can't do with all the stuff I just described. And they also incur lots of accidental complexities. And accidental complexities are problems that can arise due to limitations with software techniques, software tools, software methods, programming languages, et cetera, et cetera. So you can hurt yourself. Think of the guy pounding his fingernail with the hammer, or his thumb with the hammer. With later versions of Java, and this is particular Java 5 or JDK 5 or Java 1.5, depending on how you like to use those terms, they added a slew of other cool concurrency mechanisms. So they added this thing called the executor framework that support thread pools. They added a boatload more synchronizers like reentrant locks and reentrant read-write locks, and semaphores, and condition objects. They added blocking queues, atomics, concurrent collections like concurrent hash map and so on. Those things became available in Java 5. And they are very cool, and they support something that's called coarse-grained task parallelism. And so the idea is you break your program up into tasks, and you can submit them to run in a pool of threads, and you typically tune the pool of threads to be about the number of cores or CPUs on your machine. And so it gives you this coarse-grained processing capability. So multiple tasks can run concurrently. And the assumption, keep in mind this was 2004, 2005 timeframe, the assumption of the day was there were 2 to 4 cores or 2 to 4 processors. That was about the extent of what most people had access to. So it was fairly coarse-grained. Here's a simple example of this, where we're going to have a fixed size thread pool that's going to coordinate the starting and stopping of multiple tasks that acquire and release shared resources. So this is an example called the Palantir Manager application. I have a whole slew of assignments for my other course where we do this in all kinds of cool ways, but here's a quick way of doing it. You can make a fixed size thread pool where you have as many threads as there are beings from Middle Earth that want to gaze on a smaller number of Palantiri. So now we're into Lord of the Rings as opposed to Harry Potter. And then we make ourselves a couple of barriers. We have a cyclic barrier to keep track of starting all the beings gazing at the same time. And we have another barrier that's called an exit barrier, which is a countdown latch, which is going to keep track of when the beings are done gazing. And then we basically iterate through a loop, and we make a runnable for each being, and we tell that runnable to be executed in the fixed size thread pool, and that queues up the runnable, and then it'll run when there's an available core to process it. So that's just a very simple example of using the Java 5 era concurrency and synchronization primitives. These primitives are feature-rich, they're very optimized, but they're also tedious and error-prone to program, which can be inconvenient. And the other problem with this style of programming is it doesn't scale up very well on modern multi-core processors, where we have a lot more than 2 to 4 cores. So just as an example, my humble MacBook here has 10 cores, which is pretty cool. But if you take a look at server class machines, they can have dozens of cores. So unfortunately, the ability to take advantage of the cores was being left behind because the programming techniques of the day were not sufficiently scalable to make them work. Of course, that motivates all the stuff we're going to focus on in this class, which is Java's modern support for parallel processing, asynchronous processing, and reactive processing, which are all variants of parallel processing. So we'll talk about that stuff in a lot more detail here very shortly. So that's the end of the history of concurrency support in Java. So this is sort of the end of our overview of concurrency. The rest of the course will be focusing on parallelism, but I wanted you to at least know some of the concepts of concurrency, because if you don't take another course on concurrency, that way you will have at least had a day or so of discussion of those topics.